We'll talk about pass by value. So there's two ways that a program, a method, can be passed arguments to. The one way and the default way. What happened? The default way is by value. There's another way called by reference, and we'll talk about the two later. And basically, when you pass by value, let's bring that one up. That was test pass by value. There's not much really to show you what's going on here, because it's always going to do it that way, meaning that what we've seen so far, everything that's been passed so far has been passed by value. So it's really just demonstrating how memory works by default when you pass arguments. So I think what it's going to show you here is that we are going to we have a method here, a void method, which means it returns nothing. We're going to pass two numbers to it, and it's going to swap the numbers, right? And it's going to use a temporary int to swap them, because you need a temporary placeholder, so that temp becomes n1, n1 becomes n2, and then n2 becomes temp, which was originally n1. And it's going to print out after swapping them inside the method, right? So up here in the main, it's going to show you before invoking the method, after invoking the method. And we'll go ahead and run this, but what you're going to see is that you're only going to see these numbers swapped once. Okay, the first time, the numbers haven't been touched. The second time, which will be in swap, they haven't been touched yet either. Now here, they've been swapped. So on this printout, it's going to show you the numbers in swapped. But when we come to the final one, it's going to be like swap never happened. And that's because essentially it didn't. Passing by value means that when you call a method, swap in this case, and you pass it some arguments, that swap gets a copy of that data. So n1 and n2 have the values of num1 and num2, but they're in different memory locations in the computer. So whatever the method does with those values, it's doing it with its copy of those values. So it's like making a photocopy of a page and giving it to your friend. If your friend marks up, or you use a bunch of highlighter on the copy you gave him, that doesn't magically mark up the original. And the same thing is happening here. Main is giving swap a copy of these variables, not the original. So we'll go ahead and run and we'll see what we mean by that. Okay, so before invoking the method, it's 1 and 2 as expected. Inside the swap method, before swapping them, it's 1 and 2. And then we see after swapping them, it's now 2 and 1. But back in the main method, it's back to 1 and 2. So this is an example of pass by value, and this is the default behavior on memory for what we call primitive types. This actually, the default behavior changes a little bit when we go to objects, proper objects. But in default types, primitive types like ints and chars and doubles and floats, that's the behavior. The method that you're calling gets a copy, right? You know your friend is going to mark up the notes, your class notes, and you want the class notes for yourself, and you don't want your friend to mark them up, so you make a photocopy of your class notes. You don't give them the original, right? And basically the same thing is happening here internally. That value is being copied, but it's not the original. Um, let's see. So this kind of goes over it again, and this is sort of basically the same thing again. As we start, as main is invoked, num1 and num2 are created in a memory location that main has access to, and they're given values 1 and 2. As the swap method is invoked, it creates its own variables, and these are different variables, n1, n2, that have the same values, 1 and 2, and temp that has nothing. After it executes, this memory, all this memory created by swap2 is tied to swap. It's tied to swap's lifeline, meaning that once swap hangs up the phone, so to speak, all the memory that swap created is gone. It's completely gone. It's like the call never happened. So this is very temporary memory. And then back in main, which is still there, living and breathing, the memory is still available. Of course, the main will eventually stop as well, and then all the memory it allocates or requests goes away as well. So this is kind of like some basic ideas of memory management. Higher level languages do most of the work for you. Don't really have to worry about it too much, but it is an important topic. A couple of other examples. Methods can be used to reduce redundant coding to enable code reuse. We know that. Methods can also be used to modularize code and improve the quality of the program. Okay, so let's look at greatest common divisor method. Here. GCD as a method. We did something like this the other day, but I think it was done all as one in one program. So now GCD, it's a method that does a very simple thing. It determines the greatest common divisor between two numbers. And we did this example the other day, but we just didn't do it in a method. And now we're putting it into a method. And that's a good idea. Something generic that you think you might use a lot, like a generic method that does a greatest common divisor, that's something that might be reusable. You would want to put it into a method. And you want to make it generic so that it's reusable. And it should only do greatest common divisor and nothing else. Then we get the numbers from the people, and we can do this. And we can keep on doing it over and over and over again as many times as we want, which will give us the GCD, or greatest common denominator. So if I put 10, and if I do this, 10 is going to be the greatest common denominator, right? Oh, I did 50, it's 10, okay. But if we do, let's say, 9 and 27, we get 9, because 9 goes into 27. And then other things as well. If we were to do 12 and 11, we'd get 1, because there's nothing common between them two. But if we did 12 and 14, then we'd get 2. Or if we did 12 and 16, we'd get 4. Okay. So that's modularizing these things and making them reusable. It's a really important concept of programming to do that. Prime number method. Let's take a look at that one. I'm not sure if I got that one or not. Oh, there it is. No, nothing. But we did something like that the other day, didn't we? Let's just bring it in from here. Main method. Okay, so is prime. No, this thing already used a method. Yeah. So we'll. So this thing just checks to see if it's prime. We already really had this last week, so let's just or a couple of days ago. Let's move on. Decimal to hex. This is kind of a neat little one. I'm not sure how much you guys know about different numbering systems. Does anyone learn hexadecimal? What hexadecimal is? Octave? Not seeing any hands go up. I'm guessing that's no. Decimal to hexadecimal. So, what this means, and this is commonly used, or it used to be used a lot more in older languages, and I think I talked about it a little bit when we talked about assembly language on the first or second class, is that they had different numbering systems. The one we're most used to using is the decimal system, which is essentially 0 to 9. It's not 1 to 10, by the way. It's 0 to 9. At least in computer terms, it's 0 to 9. And we also learned binary, which is 0 and 1. Octave is 8, which means your numbering system goes 0 to 7. And this was because, 8 bits to a byte, so there was a reason for it. And then there was hexadecimal, which is double that, it's 16. And again, because you started having 2 bytes being important. So, which meant you could reference the maximum value of 1 byte with octave and 2 bytes with hexadecimal. So how does it work? Well, if you have a hexadecimal number, what is 9? Well, it's still 9. 0 through 9 are the same. But then when you go to 10, in decimal, it would be 10. But, and we could probably do a quick chart here, which probably would be a good idea to keep somewhere along the line. Just something here. Oh, I'll go hexadecimal. Actually, let me go and do. So we can see some bigger numbers. Okay. Any questions so far? What we talked about? Oh, it's a different word processor. Ah, there we go. Alright, so let's make this a kind of a large font. So here we're saying that under decimal, you've got this. Zero, 1, 2, 3. Now you go to the next one, which is going to be 10, 11, 12, 13, 14. And let's go down one more. I'm just going to go to 20. Oops. So in hex, what does it look like? 0 through 9 are the same, so I'm not going to bother doing there. But in decimal, when we get to 10, it now takes 2 digits, 10. Well, that's not the case in hex. In hex, they reference the numeric value 10 as A. 11 as B, C, D, E, and F. And guess what 16 is? 10. It's not 10, it's 10. So hexadecimal, when we say 16, base 16, that means that you've got only one character for the first 16 values. Right? So then when we get to 17, it's now 1, 1 in hex. And we don't say 11, we say 1, 2. That's hexadecimal. Keeping track of how this all converts can be tricky.